owners of the land on which I'm streaming to you from. I work on the unceded lands of the Wurundjeri people of the Kulin Nation, and I pay my respects to their elders, past, present, and emerging. And I invite you to maybe pop into the chat where you're joining us from. I think it's important that we acknowledge that First Nations people were the first scientists of this land. And for tens of thousands of years, they've been observing the land, the sky, and the sea, and passing down the knowledge that they gained in doing so from generation to generation. Indigenous knowledge crosses many scientific disciplines, from engineering to ecology and medicine to astronomy, and that leads us really nicely into today's topic, which is very much an interdisciplinary sort of science, data science. It's an amazing field that brings together mathematics and computer science, along with biology, physics, chemistry, policy, finance, climate science, all the sciences, so many different fields. I think that the people who work in this area to bridge all sorts of sciences together are just absolutely brilliant. So therefore, it is my absolute pleasure to introduce our two speakers today, Dr. Chris Baker and Isobel Abell, both from the School of Mathematics and Statistics. Dr. Chris Baker is a research fellow affiliated with the Melbourne Centre for Data Science and the Centre of Excellence for Biosecurity Risk Analysis. And Isobel Abell is a PhD student, having recently completed her Master of Science majoring in mathematical biology. Chris has worked on biosecurity management problems, and both Chris and Isobel have also been part of a team of researchers modelling the dynamics of COVID-19 to help inform government policy in collaboration with the Peter Doherty Institute for Infection and Immunity. So super keen to hear about that today. A key aspect of this modelling work is in connection with the Department of Foreign Affairs and Trade, and they really help us understand how vaccine strategy interacts with the size of previous COVID-19 outbreaks, how that interaction impacts vaccine policy and the clinical outcomes of future waves. So very, very relevant to today. Just thought I'd start off with a very, very short song about what they do. You might recognize the tune, but the words are a little bit different to maybe what you're used to. Chris and Is use mathematics and collab with other sciences. Together, they can take it higher. Together, they can take it higher. Data science is everywhere. They track COVID-19 outbreaks for us. Together, we can take it higher. Together, we can take it higher. Okay, that's enough of me. I'm going to pass it over to them, but I highly encourage you to send any questions you have for Chris and Isobel using the chat down below. And we'll also have a poll question or two for you as we go. So now I'll hand over to Chris and Isobel.
Thanks so much, Kath, for the welcome. And yeah, thanks everyone for joining us today. So as we heard, we're going to talk a little bit about all the crazy places data science can take you. But to start, I wanted to give an acknowledgement of country. So I acknowledge that we are meeting on the lands of the Wurundjeri people, and I pay my respects to their elders, past, present, and emerging. I also acknowledge that Indigenous people are Australia's first scientists, maintaining and sharing knowledge through an oral tradition that has been practiced for generations. So to kick off our talk today, I wanted everyone to pop into the chat all the different places you think data scientists might work, the different fields, whatever that might be, while I start talking a little bit about what data science is. So I think we all engage with some aspect of data science throughout our daily lives. And one of the big areas that we probably do that is through image recognition. So maybe you type into Google, I want a picture of a rabbit or something. There's something to do with data science, figuring that out for you and turning that query into something that you can interact with and what you want. And there's lots of people working on different types of machine learning models or artificial intelligence to help with things like that. Another one might be if you're in a pub and you want to know the song that's playing, you might get out your phone and get the Shazam app or something up, and it will listen to some of the audio that's happening. And if you're lucky, it will tell you, this is this song. But data science is a bit more than that sort of machine learning, artificial intelligence that a lot of people might think it is. And actually, when I started at the University of Melbourne, a few years ago, data science didn't even exist as a program that you could study. So I studied mathematics, and I started in applied mathematics, where we focused on thinking about the mechanisms of how the world works to try and get a better understanding of everything. But as I sort of went on throughout my career, I've started to incorporate other areas of mathematics into my work. And a big part of that has been statistics. And I think that's kind of where data science sits. That we're trying to use our understanding of what the world is and how things change, but bringing in using whether it's statistics or machine learning, a better understanding, or incorporate data in a better way into that. And so, yeah, so that's some of the things we're going to talk about today, is how we use data science and approach that in our work, which might be a little bit different to what you would see in the world around you. And even though I sort of mentioned before that these machine learning algorithms, whether it's image recognition or to do with audio, some of these really do have a lot of roots in different areas of mathematics. So Shazam actually comes out of, at least partly out of applied mathematics. So we're really drawing from a lot of different fields. So as Catriona mentioned, I tend to work in the biology space. And two of the big applications I've worked in the last 2 years is firstly in COVID, trying to understand day by day what the new information means and what that means about how we can manage what's going on. And the second place that I work is with CEBRA, the Centre of Excellence for Biosecurity Risk Analysis, where we try and help the government through Department of Agriculture, Fisheries and Forestries understand what's happening and use mathematics and statistics and data science to help them do a better job of managing our biosecurity. And one of the questions that sort of links these two areas is, how do we know if something is there? And this is the question that sort of carried me throughout my career a little bit. And in some ways, it's a kind of silly question. Like, how do I know if something's there? What about my car? Well, maybe I'll go to the garage, see if my car is there. But if it's not there, does that mean I don't have my car? Well, maybe my partner took my car and parked it somewhere else, and maybe I still have it. So just because you can't see something in the first instance doesn't mean it's not here. And this question has taken me quite literally around the world. And one of the places I got to travel to was Santa Cruz Island in California in the United States. Back then, I was doing a lot of work around ant eradications. And so I went over there to discuss, are the ants there or not? Well, they go out with lures, they break the island into 50 by 50 meter grid cells. They put down little pieces of paper with peanut butter on them, wait for half an hour and see if any ants find them. Well, if you do that and no ants come, are they there? Well, maybe. You come back the next year and do it again. And after a few years of that, you're sort of building up more and more confidence that they're not there because they haven't found the peanut butter yet. But what we do with data science and taking this applied mathematics approach is turning that into a probability and say, well, if you've done this many times, you can be this confident that the ants are no longer there. And further to that, we try and add some ways to manage the system where you say, well, even though I'm this confident that they're not there, if I want to check again, where should I check? Because it's not going to be a uniform probability of ants popping up again all across the island. So helping managers think about, where should I focus my efforts if I was going to do that? And as I said, this question is linked to COVID work. We had a lot of time in the last 2 years thinking about how we search for COVID. So the way we do that is through testing. And I wanted to give a quick plug to an article that I wrote with my colleagues from CEBRA, Nathaniel and Andrew Robinson, about the testing strategy in Australia. So you can either Google the title if you want to find the full article, or also scan that QR code, will take you to it. And in that work, we're really trying to think about, what does the testing strategy that we're employing, or how many people are we testing, and how does that relate to how well we're doing at managing the system? And one of the things we were trying to say was, searching as much as you can isn't always the best thing to do. Because if you search too much, you test too many people, it takes a really long time to get the results, and then you're not getting the information you need quickly enough. And answering this type of question hasn't just taken me around the world. It's also taken me to rooms with people, fairly influential people, which was not expected, I did not expect when I started studying mathematics. And last year, Jodie McVernon, who leads our COVID modelling team, was listed as the 5th most influential person in Australia through the type of work that we were doing. So yeah, mathematics can take you across the world, but it can also take you into some interesting rooms where you get to meet some really interesting people and really make an impact in society. So at this point, I'm going to hand it over to Isobel, who's going to talk a little bit more about the modelling.
Yeah, so we have a question for you all. You want to know if you have COVID-19. So you've woken up with a sore throat, a stuffy nose. What are you going to do? So you could take 1 rapid antigen test. You could take 2 rapid antigen tests. You could go get a PCR test, or maybe you take a rapid antigen test and get a PCR test. So while we're thinking about this, we're going to show the results from the poll a little bit later, but I'm going to take you through how we think about this problem. So we've been talking about how do we know if something is there. Let's consider the example of COVID-19. So when we're thinking about building a model to see if COVID-19 is there, we're talking about testing. And so everything is going to be in probabilities. But there's an issue in that the world is very complicated. On the right here, we have a graph that shows how test sensitivity, so the probability of testing positive with PCR if you have infection, how that changes as you go through your infection. So when you start, when you just have COVID-19, you're very likely to test positive, or much more likely to test positive than later in the infection. So there's uncertainties like that we have to think about. Do we consider it in our model? Is that going to make it more complicated? Is it relevant for the question that we're asking? So when we're building a model to look at the probability of finding something, so testing, we usually simplify things and say, okay, what are we asking? How can we simplify it to get an answer that we know, but we know how we can interpret it and is useful for our question? So let's consider a very simple example. You have COVID-19, unfortunately, and you decide to take a PCR test. Now, let's assume that PCR test sensitivity is about 97%. So what we want to know is, what is the probability you test negative? What is the probability you have COVID-19 and you return a negative test result, so a false negative? If we have a test sensitivity of 97%, that means if you take 1 PCR test, you have a 3% chance that's negative. So that's quite small. Maybe you don't trust that negative. You think, oh, my sore throat is very sore. And you take another PCR test. Again, just with probability, we have 3% chance of testing negative both times. So suddenly you have a 0.09% chance of getting a negative test twice if you have COVID-19. And then say you don't trust that second negative. If you take a third negative PCR, which means you've waited in queues for quite a long time at this point, you're down to 0.0027% that you get 3 negative tests in a row. So what does it tell us? This tells us that PCRs are pretty good. And testing more times, maybe that won't do a whole much, because you're already quite likely to get a true positive first time around. So again, you have COVID-19. This time you decide to take a rapid antigen test. So in Australia, rapid antigen tests have to have sensitivity of at least 80%, but usually they're much higher. So what does this mean? This means that you take a rapid antigen test, you have COVID-19, but you get a negative result, and the probability of that happening is 20%. And so you get that negative result and you go, I don't really trust this, I'm going to do it again. And so you take 2 rapid antigen tests, the probability of getting 2 negative results is already down to 4%. That's quite small. If you think back with 1 PCR test, the probability of getting 1 negative is 3%. So again, maybe you've got 2 negatives in a row for your rat and you still don't quite trust it. And so you take a third rapid antigen test. The probability of getting 3 false negative rapid antigen tests is already down to 0.8%. So that means that you can be pretty sure by 3 rapid antigen tests that you can trust the result. So how does this actually transform into modeling? How is this useful? So a question posed at the start of 2021 was, how should we test in workplaces? So we're thinking about places like hotel quarantine, where the staff are more likely to be exposed because of the positive COVID cases in the hotel. Or maybe we're thinking about workplaces such as aged care facilities, where if someone does get COVID-19, it has quite serious consequences for infecting the elderly. And so the question we were looking at is, how do we define these testing strategies? Do we have to use PCRs, or can we define testing strategies with lower sensitivity tests? And so these are some of the results from our modeling. If we look on the left, we're looking at modeling the probability of detecting an outbreak in a workplace within 7 days. And so on the left, we're varying test sensitivity and when we test. So are we testing daily, weekly? How frequently are we testing? And so what this graph is telling us is, even with low sensitivity testing, if we're testing frequently, we would be doing as well as high sensitivity tests. On the right, we have a graph again showing the probability of detecting an outbreak in a workplace within 7 days. And instead, we're looking at test sensitivity and reproductive number. So reproductive number has been thrown around in the media a lot. In this instance, we're using R effective, which means on average, how many people is a positive case going to infect? So usually when we see a high R effective, everyone panics because it means a big outbreak and lots of cases in the community. But what this graph on the right is telling us is that high R effective is actually not bad in this scenario, because it means that you can detect this outbreak really quickly. And so if you have R effective and you're using a good isolation practice, then maybe you could avert a large outbreak quite quickly. So let's think back to our poll. What should we do if you have COVID-19 and you want to test? So this is interesting. People are saying take a rapid antigen test and get a PCR. Lots of other responses for the other options as well. There is no right answer, right? It depends on the context. If I'm going to see grandma, maybe I go take a PCR because I'm more sure that that will give me a true result. But maybe I can't take the time out to go get a PCR. So instead I take 2 rapid antigen tests. So in this way, we're really thinking about what's the context here, what is the best option for us in this moment? And there is no best option, and we've just got to think about those probabilities. So I'm going to hand back over to Chris, and now we're going to talk about how we think about emerging threats. So when we don't know if something is there, rather than COVID-19 when we know it's in Australia.
Thanks for that, Isobel. And yeah, as she said, we're going to briefly talk about foot and mouth disease. So you might have seen in the news that it's been recently announced that foot and mouth disease is arrived in Indonesia, which has caused a little bit of angst in Australia, particularly in the cattle industry, worrying about whether it will get into Australia or not. And as we just heard, there are no absolutes either. So whether it's border closures, quarantine, boot washing, which you might have seen in the media, none of these things are foolproof. And so this is the type of question that we spend a lot of time thinking about in SEBRA and trying to take a risk-based approach to how do we manage these issues. And so one way to start thinking about it is to say, well, how much time should I spend looking, or how much money should I spend in trying to find foot and mouth in Australia when I don't know whether it's here or not? And a starting point might be to estimate how much an outbreak would cost if it happened. And hypothetically, if it cost $50 billion, we probably shouldn't be spending more than $50 billion a year looking for it. Otherwise, we may as well let it happen, and we don't even know whether it's going to happen. So one way to think about how to balance costs of surveillance and management with the costs of the thing actually happening is a concept called net expected cost, where we balance the cost of search effort And to that we add how much an outbreak would cost, multiplied by the probability of the outbreak happening, given how much time we spend searching. And one of the sort of tricky parts of this is the more money we spend in the search effort, or maybe some preventative steps, both the smaller the outbreak, the smaller the probability would be of the outbreak happening, but it might also decrease the cost of an outbreak if we catch something early. But this is a sort of a basic framework of a risk approach that you might take to think about management of this type of problem. And data science is throughout all of it. We need to think really carefully about probability of detection, or how multiple search and different types of search strategies interact, whether there's multiple pathways, whether it's only going to come through a traveler from Indonesia, or whether it might come across the Torres Strait from Papua New Guinea if it gets into Papua New Guinea after Indonesia. And as I mentioned, my colleagues at Cerebro spend a lot of time thinking about this. So I'm going to put up another article that I certainly encourage you to Google. The QR code is right there too. So in this article, my colleagues wrote about a range of different steps that we're putting in place to prevent foot and mouth coming in, and how this might affect the risks of those things happening. Okay, so to finish up, we're going to go back to the very first slide, or what we mentioned on the very first slide. What are the fields that data scientists work in? We've spoken a lot about issues that really fall under biosecurity today, but it's everywhere. So whether different areas of biology, whether it's ecology or genetics, it's throughout medicine, business, technology, and many, many other areas. Really anywhere with data, which is pretty much everywhere. So to finish up, I'd like to thank Isobel for doing this talk with me, and also give a shout out to TK and Tom, who helped us in this path and getting this done. So thank you. And I'll pass it back to Catriona. Thanks for coming.
Alrighty, thank you very much, Chris and Isobel, for your presentation. Just while I wait for questions to come in, remember that you can put questions in the chat, and I'll pass them on. But I'm going to take a question from Emily and sort of expand on that a little bit. So in terms of COVID-19 testing, what about accounting for human error? So for example, when people aren't solving deep enough and things like that. And I know that you've said that things aren't foolproof, but in general, how do you factor in human behavior into models?
That's a really good question. The way testing is usually defined in terms of the probabilities, or at least at the first case, is usually in pretty ideal scenarios. And it's really true that in real world conditions, things might not work quite as well. And people will use, we'll take real world studies to try and understand effectiveness. But also what we can do is, when we have that result showing how test sensitivity affects the probability of an outbreak detection within some time frame, you can then start to understand, well, if I lost, you could say, suppose I lost 20% sensitivity because people aren't solving properly. What does that mean in terms of my probability of detection across a window? And at least in the results we showed today, if you went from 80% down to 60%, it probably doesn't really change that too much. And that's sort of the power of taking this sort of approach, is that if one of our assumptions maybe isn't quite true, you don't just throw everything out and say, oh, it's wrong. We say, well, how might that affect the system? And we can quantify what that means.
Mm-hmm. Does it mean that you have to work with a lot of people who do understand human behavior in society and things like that as well?
I think it means reading a lot about that.
Right.
I also think it comes into uncertainty analysis. And so you can never be certain about anything. And so the graphs that I showed had no uncertainty analysis. Whereas if you find a study that says, well, we think it varies by this much, and so you can build that into your model and then try and communicate the results.
Yeah, and one of the things that some of our colleagues have done a lot of throughout the COVID pandemic is through phone surveys that have been organized through the government. So colleagues will write questions asking, what percentage of the time do you wear a mask when you go to the house? Or do you keep 1.5 meters distance away? And that goes into this big model that tries to track human behavior through time, so that we can have a sort of a real-time understanding about behavior changes that are occurring and how that might map on to effectiveness of strategies or what's going on.
Yeah. That idea of like things never being certain, it just reminds me of like high school mathematics or even primary school mathematics, where like when you learn probability, nothing is ever 0 or 1. So it's just like nothing's certain. Thank you very much. We have a question from Balor, and apologies if I pronounced your name incorrectly, but Balor wonders how we could best utilize data science in the education sector. It's a big question.
I know people who think about education and learning outcomes. Not really my area, so I'm not going to be able to give a very good answer. But I know that people study how performance of people in education and looking at different types of teaching strategies and how that affects performance and learning. So that's the kind of place. And it's, I think, where data science comes into that is really analyzing the data. So you need to work with people who are like the subject matter experts, who are the people in the classroom who really understand what's going on. But then as a data scientist, you can say, help people figure out how to do an experiment to test different strategies and then analyze that data properly so that you're actually getting the right answer.
I'd say anywhere you can find data, anywhere you can point to, I can collect data that will help me understand this thing better, whether it's which teaching strategy is best in this scenario. I think Chris is right in that it requires talking to people who are experts. So we can go into a classroom and collect data and analyze it because we don't know anything about that. But finding people who are the experts and helping them design some way to find this data and then analyze it to help them do their job better, to help make education for children better, things like that. Good question.
Because you'd have to work with people who are experts in, all sorts of different fields, depending on what the project is, like whether it's, in the education sector or just looking at some of the responses of where people think, data science would come in handy, like, looking at Mars samples and things like that. So what is the typical background of members of a team such as yours? I wonder if you could sort of give us some examples of career paths.
Very varied. I don't think there's one background to data science. There's definitely no background to working with data scientists. I came from an applied maths background. I actually did pure maths in my undergrad, but went to applied maths. But TK, who was on the slide before, came from quantum physics. Tom came from pure maths. But I think in the COVID team, there's a lot of other people.
Yeah. Yeah, really, really broad. Tend to some sort of quantitative discipline, really. Nathaniel, who was on one of the articles that we mentioned, came out of, did an undergrad in chemistry and is now working in data science. Yeah, really broad. I think the main thing is really an interest to what's happening in a different field. So you need to pair that interest with mathematics and sort of getting almost an excitement about numbers with interest elsewhere and really wanting to apply that and say, well, how can I use mathematics to change something else?
Yeah, thank you. We have a question from Daryl about foot and mouth disease. So with foot and mouth disease, what entry point is calculated as the highest risk?
I haven't done that calculation, so I'm not sure I can answer that without starting an argument. But as a piece of ongoing work, Daryl. Thank you, though.
I have a question regarding, like, in terms of the fact that you do work with people in all sorts of fields of STEM. How do you go about communicating your data insights to other experts in different fields, management, different departments and government, and so many people?
I think the main thing that I try and do is start conceptual. So I think people need to have, like, within them some sort of understanding of what you're doing, even if they don't get the numbers themselves. So things like understanding assumptions in models. I can see scrolling through the chat that people are talking about test independent. So if you do 2 rats, are they going to be correlated? Because maybe I don't know, you had no saliva in your mouth or something, whatever the reason is. And yeah, so understanding that there are assumptions like that in our models and being able to think through them is really key. So that's really my starting point.
Yeah, I think we also talk a lot about how we communicate it. I think that's almost unique in the maths department. I don't think a lot of other areas of the maths department talk so much about how we present things and how we communicate things, because it is really important, because not everyone understands the maths. It's not very often that we put an equation on the screen, for example, if we're talking to a non-maths audience, because that will just be gobbledygook. But we would rather talk about how we built this model and the assumptions that go into it and things they will understand, because there is a shared understanding underlying it. So it's just about linking into that and making sure that is completely clear when we talk to other people.
Absolutely. You know, one of my roles at the university is teaching people how to communicate science in an interdisciplinary manner, and like fields like yours show us why it's so important that we're able to do that. Chloe is curious as to what the differences are between what a biologist does and what you do as data scientists or statisticians in, I guess, studies that are related to biology.
Yeah, that's a really good question. And it's almost a bit of a fuzzy line, actually. So I did my master's in mathematics, but I did my PhD in the School of Biosciences at Melbourne Uni. And then I went overseas to work in the School of Biological Sciences. And then I ended up winding back to being in mathematics again. So there's people in mathematics who are sort of on the edge of biology, but there's also people who are in biological fields who are also on the edge of doing maths. So yes, we work together, and there's not always a really clear distinction of who is in which department and which field. But one of the things that is probably a bit more indicative of being biology might be that you do experiments, or you might go out to field sites and do that kind of stuff. Well, and then on top of that, you must still do the analysis yourself if you have those skills. Well, in the maths department, we're probably less likely to be doing our own experiments, but that's not 100% true. I know at least one person in the maths department here who does experiments.
I think I just want to add to that, that if you're in maths and interested in biology, there is a pathway to doing mathematical biology. If you're in biology, you're interested in the modeling and things like that, there's a pathway to do that together, and it is a really fuzzy line. But I think the good thing is you can approach that line without having a background. So I did no biology at all, and here I am talking about testing and, you know, shedding of viruses and things like that. But that doesn't mean that we can't work in a biological field and model biological things. It just means we need to talk to a biologist.
Yeah, thank you. Garrett, clearly you don't have to pick one or the other. You can do both. Okay, no más dos. Kind of a question around the amount of data that you're dealing with and handling. What type or a size of data, I don't know if that's a good question, are you working with, and do you ever think that we'll be at the point where, you know, there's just so much that you have to handle that maybe technology can't keep up?
I think at some, well, depending on who you talk to, there are some areas where there is too much data and it's hard to analyze it because you can't put it on your computer. It has to sit on a server somewhere and you have to write code to analyze it because there's just so much. The areas I usually work in are kind of small data. That's what was sort of mentioned at the start about the AI and machine learning stuff. It tends to be big data. But there's also a side of data science, which is small data, which is given this little piece of information that we know, how do we get the best out of that thing? So I'm usually in that small size, but not always.
I think also the models themselves can become so complicated that you can't do it on your own computer. Like the Australian vaccine models are done on a supercomputer because our computers are not powerful enough because there's so many people that it's modeling.
Yeah.
So yeah, it's kind of an interesting question. I'm about to say something really funny, but I don't actually work with that much data for being a data scientist. I work much more on the modeling side, so I don't touch a lot of data. But then there are some people who completely analyze data, and that's all they do.
And are there ways that like people like myself and maybe many other people on the call who, aren't really amazing at maths, are there ways that we can help you as maybe citizen scientists?
One thing that pops into mind is flu tracking. So pop onto the flu tracking website and register. I think they send you a weekly email asking what symptoms do you have. And we use that to try and track flu dynamics and COVID dynamics now. So pop onto that.
I think it's just about thinking about one of the biggest issues we have when it comes to data is cleaning it. So, if you have a positive rat, reporting your positive rat at the time that you took it, for example, things like that, to make the data as clean as possible so we don't have to do as much work trying to infer what's true, what's had a little bit of a time frame, it's reported a little bit later than it should have been, things like that.
Yeah, I think, and for the academics on the call, if you're wanting to try and talk to a data scientist and collaborate, I'd say do it early was my tip. Because there certainly have had times where whoever it is you're talking to and says, here's the data, can you help us? And my answer, but if you talked to me beforehand, I would have said, don't collect that data. That's not going to help with the question you're asking. So conversations early and often, my tip.
There you go. Start a conversation with Chris and Isobel now. They put their contact details on the end of their slides. So do it. We have potentially a quick question, just to clarify. So is data science mainly about probabilities and making predictions with those?
I don't know if that's a quick question.
Maybe it's not. Oh, okay.
Down to exactly what it is. If I was defining data science, I would talk about it more in terms of using data to think about something, basically. Whether that is probabilities, predictions are very difficult because there's a lot of uncertainty, but I guess if you think about classification problems in machine learning, kind of prediction. But yeah, it's sort of anything to do with analyzing and using data for a purpose. That's what I said.
Yeah. So there's, I guess, kind of different branches of it. Part of it is just about, maybe it's visualizing data, probably falls under data science too. In mathematics here, we tend to work on, well, how can we do data science methods better? But yeah, it's a huge spectrum.
Or even some of the stuff that we do is just, here is a model and we can fit it to this data, which is not necessarily about probabilities in the output of the model itself, but there are certainly probabilities in how sure are we that this model fits the data and things like that. So it's about making our model more reasonable and better suited to our question by using this data that we have available.
Awesome. Ben is taking us back to school science as well, or school mathematics, I should say as well. Ben says in school, we rolled a dice and we worked out the probability of rolling, a single result from when you roll that die. So when you have a die, it's not hard to work out how many hundreds of times we need to roll to get a large enough sample size. So how do you work out sample sizes for something like COVID-19?
I think the dice is a really good analogy. So in school, maybe use a dice, but a computer is almost like a really complicated dice rolling machine. So when we have a really complicated model, we could run experiments, and maybe it takes days to do it with the computer humming away in the background to really understand how much variation there is in the model, and therefore understand how big the sample size needs to be.
I think you're talking about sample size in terms of when we have a model where the results are based on probabilities, the outputs change. Generally, if I'm running a model and I run it with 1,000 simulations, and I get one result, and I run it 1,000 times again, and I get a different result, well, maybe I should be running it a few more times. But if you're talking about sample sizes in terms of like biology, in terms of working out test sensitivities, I think back to high school with what I learned. If you're doing something for Australia, you'd need quite a large sample size, but you would need a larger sample size if you're doing something for COVID around the world. So I think the same ideas that you learn back in high school about how big is my population group, how far am I inferring this data, still applies to this sort of stuff.
Yeah. Doing STEM in high school, super important, everyone. Just seeing if we have any last minute questions, if anyone wants to, ask anything else. But as I sort of wait for that, I just really want to thank you, Chris and Isobel, for sharing how you use maths and data science to provide solutions to real world problems that are impacting us all right now with COVID, but also in the future, and thinking about emerging threats, and also really showing us how we could be using data science to work smarter, not harder. So thank you very much, everyone in the audience as well, for asking questions, for answering questions as well. And remember that you can come along to our other masterclasses. This was only one of 5. So on Tuesday, we have Dr. Vera, a paleontologist who's just back from a dinosaur dig in Wyoming. So really keen to hear all about that. On Wednesday, we've got Dr. Chris Hall, who will be illuminating possibilities for transforming light into energy and energy into light. You can also just keep coming back for more of those science puns. Thursday is Dr. Kate, who will talk about the science of bushfire risk. And on Friday, Professor Michael will be talking about the grasshopper who's given up on sex. So you can register for any or all of those using the link in the chat that Alexis just popped in. And also remember that there's lots more on at the Science Festival this week. Like I think there's liquid nitrogen ice cream and all sorts of cool things. So definitely check it out. Check out the schedule. Thanks so much for joining, and massive round of applause from me to Chris and Isobel. And I can imagine that there'd be like thunderous applause if we were here in person. So thanks very much to the two of you and all of you, and enjoy the rest of your day. Bye.